Hello again. We continue with lecture number 8. We just discussed the Jacobi method for solving linear systems. Now we will discuss the next method, which is called the Gauss-Seidel method. And we start again with the matrix A, which was the matrix associated to the system AX is equal to B. And the same as with the Gauss-Seidel method, in order the Jacobi method, in order the Gauss-Seidel method to work, we would require that the elements on the main diagonal is different from 0. If they are not different from 0, then we can rearrange the equations of the original system so that we make them 0. And even if they are not 0, as I mentioned before, in order to speed up the computation, we would like to order them in such a way such that they will be, let me remind you, this was the same observation that we did for the Jacobi method. We want to arrange them such that AII, here is the observation that we made, AII be as large as possible. Now, if we go and write down what the iteration matrix for this method is. So we represent the matrix A again as L plus U plus D, where again the D is the diagonal matrix of the original matrix A. So if the matrix A had components A11, A12, and so on, A1n, A21, A22, A2n, and so on, AN1, AN2, ANN. So what would be the matrix D? The matrix D will be the matrix from the elements on the main diagonal. And then these elements augmented with 0 will be L, this will be D, and these elements here will be the matrix U, the same as before. And so here I had written what they are, the same as before. So this is the lower part of the matrix A, everything strictly below the main diagonal. This is the upper part of the matrix A, everything which is strictly above the main diagonal. And again, as before, instead of AX is equal to B, we write L plus D plus UX is equal to B. And so we have L plus D plus D multiplied by the vector X plus U multiplied by the vector X is equal to B. So we multiply this by X and we multiply this by X, and then before we left only dx on the right hand side, on the left hand side, we left only this dx and we moved Lx and Ux to the right. Now we will move Ux to the right only. And this is what we're going to end up with. And again, since the matrix L plus D here is now actually a lower triangular matrix. This will be A11 and so on, A1n, and here we'll have AN1, and everywhere above is 0. So this will be the matrix L plus D. Now this matrix is also, ANN is here. This matrix will also be an invertible matrix because the elements on the main diagonal are different from 0. We know that the determinant of this matrix is A11 and so on times ANN. Therefore, it will have inverse. So if we multiply now both sides by L plus D inverse, we will have that X is equal to minus, because of this minus here, L plus D inverse times U, which will create a matrix. Then this will create a vector C. So we can rewrite now our equation in the form, our system AX is equal to B in the form X is equal to this matrix here, which we denote by BGS. GS comes from Gauss-Seidel, applied to X plus C. So now we rewrote the system AX is equal to B in another way, in the form X is equal to matrix times X plus C. This matrix has particular structure, and this is how it is given or derived from the original matrix A. And this matrix is called the Gauss-Seidel iteration matrix. Now, once we have the equation written in this form, then we can, from this equation, right away write down the iterative procedure. And starting with any initial guess x0, this will be exactly the Gauss-Seidel method. So we start with x0, and then for k is equal to 0, 1, 2, and so on, we have that the k plus first iteration of the Gauss-Seidel is equal to the iteration matrix of Gauss-Seidel applied to x at iteration k plus c, where the matrix, the Gauss-Seidel iteration matrix, is given by this formula. Now here, there is not a nice representation or a nice way to write down the Gauss-Seidel iteration matrix. Moreover, it is never, in fact, used explicitly, except maybe for some theoretical discussions or error estimates. And sometimes also people, rather than moving this L plus D on the right hand side as an inverse and writing it in this form, they leave the system in this form, and then right here we know that if it is in this form, everything that is on the left side will be with index k plus 1, everything that is on the right side will be with an upper index k, and therefore one usually writes it in this form. And once you have in your hand xk, which is the approximation at step k, then you write down this system. And remember that we discussed that the matrix L plus D is actually a lower triangular matrix. You, at every step of Gauss-Seidel, can solve or have to solve forward substitution here in order to find x at step k plus 1. However, we will discuss how exactly Gauss-Seidel is performed, and for this we will look at again illustrate our method on a 3x3 system. So if we look carefully of what is in fact written here, we have, if we look at the matrix A, the original matrix A applied to the vector X. So we had here A1, 1 and A, N, N. L plus D is the lower part of the matrix A, the lower triangular matrix associated with the matrix A, and U is the upper triangular part associated with the matrix A. So here, this is what U is. And you see here that U is on the other side, U goes on the other side with an index K. So everything that is above the main diagonal is associated with an index K, and then it will move to the right. And everything that is on the main diagonal and below the main diagonal will be all the x's that are associated with A's that are in this red triangle here will be associated with an upper index K plus 1. So let's see exactly what this would mean for the 3 by 3 matrix. So this was the original system. And we see here the elements on the main diagonal and below the main diagonal. So these are the L part of the matrix A that is associated with L plus D. The elements on the main diagonal is strictly below the main diagonal. So those basically will stay on the right-hand side and we'll have the index K plus 1. So this will have an index K plus 1. This will have all the x's that are multiplied by the a's that are elements in L plus D will have an index K plus 1. This will have an index K plus 1, and this will have an index K plus 1. Everything that is strictly above the main diagonal will have an index K that are associated with, that are multiplied by entries of the matrix that are strictly above the main diagonal will have an index K. So here, this will have an index K. Okay, and now what we can decide to do is we can decide to leave, and you will see why. We can decide to leave the elements on the main diagonal, only the elements on the main diagonal, which are those elements here, the red ones, on the left, and move everything else to the right, but keeping their upper indices. So you see here that we have A1, 1x1, K plus 1. So K plus 1 is we keep the index. And then everything that is off associated to entries of the matrix A that are from the upper part of A are with index K. So this moves to the right and it is with index K. Here is the index K and here is the index K. Now we have A22 x2k plus 1, which we leave on this side. And then we decided to move this one on the right, but it will be index K plus 1. So we have minus A21 with index K plus 1. And we have here minus A23. And again, this index here is inside, not outside. This is a typo. So this is moved, and then we move this on the right. We leave A22 x3k plus 1, and then we move this and this to the right. But when we move them to the right, you see that the indexes, the upper subscript k is k plus 1, and I put them here in red. So why did we decide to do that? We basically have all the elements on the main diagonal with index K plus 1, upper index K plus 1 on the left. So this is on the left side. And on the right side, what we have with this is the vector B, which is the right-hand side of the system, minus the elements, the x's that are associated with a's that are above the, strictly above the main diagonal. They have indices K, as you can see here. This has index K, this has index K, and this has index K. Then all the elements, all the x's that are multiplied by a's that belong to the matrix L, that is strictly below the main diagonal, they have all indices K plus 1. So you see here, this has index K plus 1, this has index K plus 1, and this has index K plus 1. Now, what is the different from Jacobi in Gauss-Seidel? What is different in Gauss-Seidel from Jacobi is that the component xik plus 1 is used as soon as it is computed, and this is the difference from Jacobi. So you see here on the first row, we compute the component x1 k plus 1. And now when we go on the second row to compute x2, the second component of the vector k plus 1, we are already using this. We are using x3k because we have not computed x3k plus 1. But we are not using x1k. We are using x1k plus 1, which we have computed from the previous row. Now, if we go to the next row here to compute now x3k plus 1, the third component of the vector, the new vector, the vector at stage at the iteration k plus 1, then we see here that this vector involves the second and the first coordinate of k of the vector k plus 1. So we start directly computing using x1k plus 1, which is already computed here, and we have to we start using x2k plus 1 that is computed here. In Jacobi, here we use the old versions of x1 and x2, the versions from the vector k. In the Gauss-Seidel, we use the new versions of the first and the second coordinate of the vector. So as long as we have a better version of the better computed version of the first and the second coordinate, we are using them. And so if we would like to see exactly what is happening is the following. First, we start with when we enter the iteration, we know that from the previous iteration, we have the vector xk, which has components in this particular case for a 3x3 matrix, x1, x2, and x3. Here, after doing the first row, the operations of the first row, we compute x1k plus 1. But so we compute the first component of the next vector, but we have not computed the second and the third component. Then we come to the second row, here to the second equation, and the second equation computes the second component of the vector k plus 1 using the first component of the vector k plus 1. And now the x3k is still not computed. And then when we look at the third equation computes the third component of the vector k plus 1. So after the third equation, we have all components of the new of the updated version of the vector of x k plus 1 computed. Now we see here that in we can save a little bit of a memory here because we need only one variable x, only one-dimensional array at all times, because if you think of this as memory cells, in this place you put the first coordinate, in this place you put the second coordinate, in this place you put the third coordinate. After when we compute the components of the next approximation, then we can use the same memory cell, because here instead of x1k we will overwrite and we will put x1k plus 1. Then once we use, after we run the second equation, we will overwrite x2k and we will put here x2k plus 1. So now we'll have part of the components. Here we will have the first component of k plus 1. Here we'll have the first component of k plus 1. And here we will have the kth component of, we'll have the third component of k. At the end, we also will override this, and in this place, we will write the third component of k plus 1. So at all times, only one variable will be needed. And now, if we would like to run exactly the same example as before, as we ran for the Jacobi, we know how to do it. We know that everything on the main diagonal and below the main diagonal, we have index k plus 1, and everything above, strictly above the main diagonal, will have index k. So this will have index k, Here will be k plus 1, here will be k plus 1, and here will be k plus 1. And then if we want to rewrite it, everything on the main diagonal we will put on the left, and everything that is off the main diagonal we'll put to the right with the corresponding indices. So we move this to the right, and then we move this to the right, and this is what the Gauss-Seidel iteration will be. We know that the exact solution is 1, 1. And if we start with initial guess 0, 0, we can fill in the same table as before. So if we fill the same table as before, what we're going to have if we start with 0, 0. So here we will have 2x1, 1 is equal to 1. So from here we'll get that x1, 1 is equal to a half. And then we'll have 2x2, 1 is equal to 1 plus, now in the Jacobi, we use here 0, which was the component, the second, which was the first component of the 0 vector. But now here we will use 1/2 because we already know it. And so it will be plus 1/2. And therefore, we will get that the second component of the vector x1 will be equal to 3/2 divided by 2 will be equal to 3/4. So now here we'll have 3/4. And then if we look at the error, I will have the vector 1, 1 minus the vector 1/2, 3/4. And then we'll have the error with components 1/2 and 1/4. And therefore the infinity error, the infinity norm of the error will be a half. Now, if we do the next iteration, we will have 2x1, 2, when k is equal to 1 here, will be equal to 1 plus x2, 1. x2, 1 is 3/4. It is right here, 3/4, and therefore we have that x1, 2 will be equal to 7/4 divided by 2 will be equal to 7/8. And then we use 2x2, 2 will be equal to 1 plus the first component, which we already computed, which is 7/8. And therefore we'll have that the second component of x2 will be 15/8 divided by 2 will be 15/16. So this will be 15/16. And now if we compute the error, it will be 1 minus 7/8 and 1 minus 15/16. And the infinity, the L infinity norm of this error will be 1/8. And one can also compute what will be the components x1 and x2 of the third output of the iterative procedure. If you compare this table with the table before, you will see that the first component here will converge to 1, and the second component here will converge to 1, which are the first and second components of the exact solution. And this convergence is faster than the convergence in the Jacobi. So if you look at this table, and then if you go back to the table, the same table, but for the Jacobi method, then you will see that the convergence, it is in the Jacobi method is slower. So you have 0, 1/2, 3/4, 7/8, for example, for the first component. And here we have much faster, we're approaching 1 for both coordinates much faster than we actually did for the Jacobi method. And so for this particular example, the Gauss-Seidel method converges faster. And if we compute the matrix, so the formula for the Gauss-Seidel was minus L plus D inverse times U. And if you compute the inverse of L plus D, if you compute U, you will find out that the Gauss-Seidel, the matrix, the iteration matrix for Gauss-Seidel is this matrix. So if we look at the infinity norm of this matrix, you will see that Here, the sum of the absolute value of the components is a half. Here on the second row, the sum of the absolute values of components is a fourth. And then the maximum of those will give you 1/2. So the infinity norm of the Gauss-Seidel is 1/2. If you look at the spectral radius, this is an upper, this particular one ended up to be an upper triangular matrix. The eigenvalues are the elements on the main diagonal. So the eigenvalues are lambda 1 is equal to 0 and lambda 2 is equal to 1/4. You look at the absolute value of these eigenvalues and you take the maximum of this and you see that the spectral radius of this matrix is 1/4. In contrast to the spectral radius of Bj for this particular case, which was 1/2. If we look at the error estimate, here is if you look at the error estimate, it follows that here should be Gauss-Seidel. That the Gauss-Seidel method converges for the any initial guess, because if you have here, and this is also Gauss-Seidel, because you see here that the infinity norm is less than the infinity norm, here is infinity, the infinity norm of the Gauss-Seidel matrix, which is a 1/2. So you will have from the theorem will tell you that the behavior of the infinity norm of the error ek plus 1 is less than or equal to 1/2 to power k plus 1 of the infinity norm of the error at the beginning, at the initial step, the 0 step. But in our example, with our initial guess, we are observing that here the actually the infinity norm of the error at step k plus 1 is 1/4 the infinity norm of the error at step k, roughly. And you can see here 1/2 times 1/4 is 1/8, 1/8 times 1/4 is 1/32, and so on. So this bound, this error bound that is given by the theorem is actually not a sharp bound for the Gauss-Seidel method in this particular case. It is a bound which will guarantee convergence, but this is not the best bound there. And if you remember when we discussed spectral radius, we discussed that, did I put it? No, I didn't put. When we discussed spectral radius, we discussed that the EK, the infinity norm of EK, or any norm of EK, in this particular case will be the infinity norm of EK, is behaving like the spectral radius of the matrix. So here will be the spectral radius of BGS 2 power k times the error, the original error. And we discussed that. I want just to show you at the beginning of the previous lecture, of lecture number 7, and I still have my write-up here, so I am going back to show you exactly where we discussed it at the beginning of the previous lecture. So we see here that the error, the norm of the error at step k behaves like the spectral radius to power k times the error. And so this gives us an explanation why the Gauss-Seidel method will converge here faster than the Jacobi method, because the spectral radius of the matrix Bj for that particular system was 1/2. And the spectral radius here, it is 1/2, while the spectral radius for the Gauss-Seidel, we just found out for this for the same matrix, the spectral radius for the iteration matrix for the Gauss-Seidel is 1/4. And because of that, we will have a faster convergence in the case when we apply the Gauss-Seidel iteration method to find the approximate solution to our system. That's why we have a faster convergence. And we also can give some sort of explanation in in this particular case. So if you look at the matrix A, and if you look at the iteration matrix of the corresponding Gauss-Seidel method, then we said that the eigenvalues are 0 and 1/4, and one can compute that the corresponding eigenvectors are V1 and V2. And if you look at the error, error is x minus x0. X0 is the vector 0, 0. So when you look at the error, you can see, why did I put here 1, 2 transpose? X minus x0. Let's see, why did I put x minus? So the vector x here is the vector 0, 0, and x1 is equal to x2 is equal to 0. So the vector, the error is, the original error is 1, 1, not 1, 2. The error is 1, 1. And so if you look at V2 minus V1, 2 minus 1 is 1, and 1 minus 1 is 1. So exactly the error is V2 minus V1. If you look at the error E1, we know that when you have any iterative procedure, the error at step 1 is equal to the iteration matrix applied to the error at step 0. So you have the iteration matrix applied to V2 minus V1. And this iteration matrix applied to V2 is equal to the eigenvalue, because this is the eigenvector associated to this eigenvalue. And lambda B applied to V1 is lambda 1 V1, but lambda 1 is 0, so this will be lambda 2 V2. And in general, if you have, one can argue that by induction, if you look at the k plus first, the error at the k plus first step, this is the Gauss-Seidel, the iteration matrix applied to the error at the k step, which is the error at the k step will be lambda 2 to power k V2. Then lambda 2 goes out because this is a matrix. Then B, the iteration matrix applied to V2, which will be lambda 2 times V2. And therefore, as a result, you'll have lambda 2 to power k plus 1 times V2. And therefore, if you look at the infinity norm of this vector, this will be equal to the infinity norm of this vector, but the infinity norm of this vector, we can pull out this number in front. And so it will be 1/4, because lambda 2 is 1/4 to power k plus 1 times the infinity norm of V2. So indeed, we see that the error here in this particular case, it is equal to 1/4 to power k plus 1, where 1/4 was the spectral, 1/4 was the spectral radius, and therefore this gives an explanation why the Gauss-Seidel in this particular case converges faster, and it converges faster because the spectral radius of the Gauss-Seidel iteration matrix is 1/4, and it is better, smaller than the spectral radius of the Jacobi method. Now, next, if you remember when we talked about the Jacobi method, we discussed and proved the theorem that if you have the system AX is equal to B, and if your matrix is strictly diagonally dominant, then the Jacobi method converges for any initial guess x0. And we, in fact, proved that using the particular form of the matrix Bj in the case when A the matrix Bj, and using the fact that this matrix for if the original matrix is strictly diagonally dominant, then the infinity norm of this matrix is less than 1. Well, similar theorem holds for the Gauss-Seidel method. In the case that the matrix A associated to the system AX is equal to B is strictly diagonally dominant, then the Gauss-Seidel method converges for any initial guess x0. We're not going to prove this theorem, but this theorem is good to know. And how would the Gauss-Seidel, how would the algorithm for Gauss-Seidel work? As I mentioned before, we do not have here two one-dimensional arrays that will store two consecutive approximations to x. We'll have only one. And I would put even not here x0, there is no x0 here. We'll just have one. X is equal to x0. And then we will have the loop that will compute the components of this vector. And as we discussed, once we run this loop, what will happen? So here these will be the n components of the vector. Somewhere in the middle of this process, when we start, so when we start, we will have here everywhere will be the components of x0. Once we run the first loop, then we will compute the x1. So this one now, after running this for I is equal to 1. So after computing this formula when I is equal to 1, we will have the first component of the vector x1. So here will be x1, 1, and the rest will be x0, 2, and so on will be x0, n. Then when I is equal to 2, this we will overwrite in this cell. Instead of having x2, 0, we will have x2, 1, and then the rest will be components that will be the components of the zeroth vector. I believe I wrote it here. No, I wrote it later, but nevertheless. So what is happening here, that somewhere in the middle in this loop, you will have one vector, and part of the vector here will have the components of the vector xk plus 1, let's say from 1 to the jth component of this vector, and the rest of the components will be the components of the vector xk. So here are components of the vector xk. Component by components, I mean coordinates, components of the vector xk plus 1. And if you look carefully, this is exactly, here is exactly what we had observed and discussed in the 3x3 case. Here we wrote it explicitly in the 3x3 case, and we see here that on the right-hand side, you are using the component as soon as you are as you have computed it. The same thing here, you use the component x1 and x2 as soon as you have computed it. So indeed, if you look carefully in this algorithm, then the algorithm, using the fact that it overrides the new, once xi is computed, it overrides this xi over the old xi, then this will be the Gauss-Seidel algorithm. And as you can see here, we are not using anywhere the explicit form of the iteration, Gauss-Seidel iteration matrix. Everything is implicitly incorporated in this loop. And again, because nothing is basically different than the Jacobi, with the only difference that we have here the overwriting. But in terms of operation count per step, the operation count per step is the same as in the Jacobi method. We have for each I, we have n minus 1 multiplications that come from this sum. And since we have I runs from 1 to n, we will have n times n minus 1 multiplications. We have, for every I, we have 1 division. Therefore, for n i's, we'll have n divisions. And we will have, because we have n terms here, we'll have n minus 1 subtractions. Since for every I, we have n minus 1 subtractions, I runs from 1 to n. So we'll have n times n minus 1 subtractions, and therefore we will have at the end approximately 2n square flops per iteration. Or if you talk about only multiplications and divisions, we will have n squared multiplications and divisions, because it will be n squared minus n plus n, which will give you exactly n square multiplications or divisions. Now, these are the two methods so far, Jacobi and Gauss-Seidel, and the question is, can one design an algorithm which makes the computation faster, in the sense that for the smaller value of k, so after less computations, you will get closer, xk will get closer to x for smaller values of k. We will approximate k faster, you will approximate x faster using xk, and therefore, since this will be faster, then you will stop earlier. And you will get a good approximation for the exact solution, or you can continue a certain number of steps, and then you will get better approximation of the exact solution. So if we look at the Gauss-Seidel, let me remind you again, to do the Gauss-Seidel, we have the representation of A as a strictly lower triangular matrix, plus a diagonal matrix, plus a strictly upper triangular matrix. So this is the U strictly upper triangular and the L strictly lower triangular matrix. And we rewrote the matrix A as L plus D plus U, and we left L plus D on one hand side, and we moved UX on the other hand side, and everything that was left on the left hand side we associate with index k plus 1. Everything that is on the right hand side we associate with index k. Now, what we do, and this may sound artificial, what we're doing here, but I will return back to it. When one investigates the behavior of the residual during the successive computations of the coordinates of the k plus first approximation, xi k plus 1, and you remember that when one investigates the behavior of the residual during the successive computations of the coordinates of the xk plus 1, but you remember, let me go back and I will explain what I mean here. You remember when we were talking about here that every time when you do, so this basically is one iteration, this whole process is one iteration of Gauss-Seidel, but in this one iteration, you one by one update the coordinates So first you update the first coordinate to make it the first coordinate of k plus 1. Then you update the second coordinate and so on. Then you update the third coordinate. So within one iteration of Gauss-Seidel, let me go back here. Within one iteration of Gauss-Seidel, you will have a vector that is something like that. The first I minus first components of this vector will be the components of the xk plus 1, and the rest of the components from ith to nth will be the components of xk. And so now this creates a new vector, which we will denote by xk plus 1 I with index I. This is a new vector because it has part of the components of xk plus 1, and it has part of the components of xk, namely the first I minus 1 components of xk plus 1, and the rest of the components are the components of xk. Now, this vector also can be used to approximate x, and therefore we can look at its residual. Namely, we can look at the b minus a applied to this vector, which tells us by how much this vector fails to satisfy the system. And recall that there was in the lecture last week, we discussed, or maybe the week before, we discussed the relation between the norm of the residual and the norm of the error, and that we are interested in finding a vector for which the residual has a small error, because this small error could be magnified by the condition number of the matrix, but nevertheless, it is good to have a small norm of the residual. And so when we look at these vectors, xk plus 1i, one finds that one can reduce the norm of this residual and therefore obtain faster convergence if one introduces a new parameter. And these methods that are based on introducing a new parameter whose role is to reduce the norm of these residuals, these methods are called relaxation methods. And the parameter in the relaxation methods is omega. And when omega is between 0 and 1, these are called under relaxation methods, and they can be used to obtain convergence of some systems that are not convergent if you use the Gauss-Seidel method, because the matrix that you end up with, BGS, will not have the properties that will guarantee the convergence. And when omega is bigger than 1, they are called over-relaxation methods, and they are used to accelerate the convergence for systems that are convergent using the Gauss-Seidel method. And they are called the SOR methods, or successive. S comes from successive, O comes from over, and R comes from relaxation. So successive over relaxation methods. And in the case when the parameter is equal to 1, this actually is the Gauss-Seidel method. So it is important where we introduced and how we introduced this parameter. And even though it may look kind of an artificial exactly where we put this parameter, it has quite a substantial thinking process behind it, which is involved into investigating this vector, into investigating this residual, into investigating how to reduce the norm of this residual. So I will just give the how to put the parameter, but I will not give an intuition why we put it in this particular place. So let's go back to the Gauss-Seidel method. This was the Gauss-Seidel method. And then what we can do, we can artificially, and here it is written in blue, add and subtract d applied to xk. You see here we have dxk and here we have dxk with a negative sign, so we basically have not changed anything. And then what we do is we put the parameter omega right here. So we put right here a parameter omega. And this is our parameter that we were talking about when we discussed the successive over a relaxation or the SOR method. So you see that when omega is equal to 1, this method, actually we can go back to crossing the D, and this method was exactly the Gauss-Seidel method. So when omega is equal to 1, the successive, the SOR method is the Gauss-Seidel method. So now once we look at this representation and we know that omega is the parameter, then we can go back and group everything with index k plus 1 to the left. So we can move minus WLXK plus 1 to the left, which will become WL, and we will pull out XK plus 1. And then we can group everything that has a K here. So what has a K on the left side is the D. Let me see if I can put the blue without. Okay, so what has K here? This has index K, and then this has an index K. And we see here that we have D, and then we have minus omega D. So D minus omega D, this is the part that is combining having D, and then we have U minus U times omega. So minus U omega, and then we pull out xk, and then minus omega times minus b gives you omega b. And then let me remind you also that if you look at the matrix D plus WL, how does this matrix look like? Well, D was the matrix with main diagonal, with it was the diagonal matrix with a diagonal, the diagonal of A, and then L was the completely lower, the lower triangular matrix that has all the elements of A strictly below the main diagonal. So then yeah, we'll have here omega A to 1, and so on, omega A and 1, and so on, omega A and minus 1. So this will be the matrix D plus omega L. And notice that this matrix also will be invertible. Again, this SOR method is used when I is different from 0. Will be an invertible matrix because all the elements on the main diagonal are different from 0, because remember, the determinant of this matrix is the product of the elements on the main diagonal, and if they are 0, the determinant will be, if they are not 0, the determinant will be not 0, and therefore this matrix will be invertible. So we can multiply both sides by the inverse of this matrix, and this is what we're going to get. So technically, the SOR method is the method for which the iteration matrix is this matrix B omega, where the B omega is this whole mess here. So this is the matrix B omega, and then this is the vector C omega, that is the vector in the iterative procedure, the vector C in the iterative procedure. And then how do we remember the SOR method? So we start with a matrix again. Let's do an illustration for a 3x3 matrix. So we see that if we look at this representation here, which is of this representation here, we see that everything that is on the main diagonal and below the main diagonal, so here it is on the main diagonal and below the main diagonal here, will be index k plus 1. So all the x's that are here will have an index k plus 1. And all the elements that are on the main, here, let me put red. Now, also, we will have that some of the elements, because if you look at the part here, we will have D. Oh, this is not red. You will have D also, so all the elements that are above the main diagonal and on the main diagonal also, some of these elements will have an index K. As you see here, you have here the elements in D, which will have an index K. And so we have D applied to xk plus 1. So these are the elements on the main diagonal that we leave on the right hand side. Then we have plus WL xk plus 1. So all the elements that are here, they will have W, and they will be with a negative sign. So we have here minus W A21 xk plus 1, and then we'll have minus W A31 x1k plus 1, which is this one here, and then A3, and then this will be minus W A3x2, which will be this element here. Then if you look carefully here, you will have a D times xk, so you will have also on the right side xk with the elements on the main diagonal. So this red part, you will have A11 x1k, A22 x2k, and A33 xk, which correspond to this 1 times D, or D times xk. And then what we will have, you will have minus W multiplied by D multiplied by minus W multiplied by D, and minus W multiplied by U. So within the minus W, you have the elements on the main diagonal here, and then above the main diagonal, which is on the main diagonal and above the main diagonal, that will have an index W. So if I go back to blue, if I manage to go back to blue without, so here, this minus WD and minus W omega, minus WU that is related to XK is this minus WD, and then the element A12X2, A12X2, A13X3, A13X3. Then you have here, this one and this one will be with index K, and then here you have just on the main diagonal, which will be this one with index K, and of course minus W plus WB minus W and minus B here will give you plus WB. So this will be the corresponding SOR method for a 3x3 system. And also for this method, you will need two variables, xold, where you will keep the x, the components of the xk, and xnew, where you will keep the components of the new iteration. They are both one-dimensional arrays. And if you look at our running example, what we'll have with our running example, that the elements on the main diagonal will be with index k plus 1. Then also the element on the main diagonal will be with index k on the other side. And then we'll have minus W, the elements on the main diagonal, and the elements above the main diagonal with index k, and then minus the B. and then the elements below the main diagonal with index k plus 1, and which is this one here, and the elements on the main diagonal with the index k with the coefficient in front minus omega. Also we know that the exact solution here is 1, 1. And if we write the matrix with all the computations and everything, we'll find out that the matrix BW here has this particular representation. So it depends on omega, and this is the first entry, the second entry on the first row, and this is the first entry and the second entry on the second row. Now one can write the algorithm, and the algorithm is first to we set x all to be equal to x0, where x0 is the initial guess, and then for I is equal to 1 to n, one can write that this x, the new, is equal to 1 minus omega xi the old. And if you look carefully at what is happening here, this is exactly what you will see. So 1 minus omega xi old, and then plus omega. And then we discussed that when everything is below the main diagonal, you will have x index k plus 1. Here, when it is below the main diagonal, you will have index k plus 1 multiplied by omega. When you have above the main diagonal, then you will have index k applied so with the index k here multiplied by omega. And when you're on the main diagonal, then you have here and then minus omega, minus omega. So on here you have 1 minus omega, and then for a to 2, and then minus omega a to 1, a to 2. So you have a to 2 x to k multiplied by 1 minus omega. Because the right hand side will be divided by this a to 2, that's why even though you see here, for example, you see here that you have a to 2 x to k minus omega a to 2 x to k. So I'm just combining those two. And then you see that this is a to 2 times 1 minus omega. Here k is in this parenthesis, x to k, but on this side you will have a to 2. So when you divide by a to 2, then this a to 2 and this a to 2 will cancel out, and then the a to 2 will come as a denominator, and that's why you will see here this denominator. So this will be the algorithm. You will find all the coordinates of the new approximation, and then you put the old approximation to be the new approximation, and repeat this process again. Now the question is, can we choose, because you see here that the matrix, the iteration matrix for the SOR method actually depends on this parameter B and on this parameter omega, and the question is, can we play with this parameter omega so that the spectral radius of this matrix is as small as it can get, because we know that the smaller the spectral radius is, the faster the convergence will be. And first there is the following theorem, which is a part of your homework to prove, and there is a hint given there how to prove it. So if you start with the matrix A with entries Aij, and if all the elements on the main diagonal are different from 0, then the spectral radius of this matrix B omega is bigger than or equal to omega minus 1 in absolute value. So what does this theorem give us as a conclusion? This theorem gives us first that the method does not converge if omega is bigger than or equal to 2 or less than 0. Why? Because let's say pick omega to be 5. If omega is 5, then what we'll have, then the spectral radius will be bigger than 4. Well, if the spectral radius of a matrix is bigger than 4, then we do not have convergence, because remember there was a theorem that says that the iteration process converges if and only if the spectral radius of the matrix is less than 1. So here we're not going to have a convergence. So the SOR method can converge. It doesn't mean that it will converge if omega is between 0 and 2, but at least it has a chance to converge if omega is between 0 and 2, because if omega is between 0 and 2, if we put a restriction here for this to be less than 1, then we'll see here that omega minus 1 is less than 1, because we want the spectral radius to be less than 1 in order to have convergence. And therefore we will have to have, if the spectral radius is, if we have convergence, the spectral radius will be less than 1. So if we have convergence, we will have to have that absolute value of omega minus 1 is less than 1, which means that omega minus 1 is between 1 and minus 1, which means that omega is less than 2 and is bigger than 0. And this is where we get this inequality that omega is between 0 and 2. So if omega is between 0 and 2, the method can, it could happen that the method will converge. But if omega is bigger than or equal to 2 or less than or equal to 0, then the method will not converge. That's why when we talk about the SOR methods, we consider only values of omega of the parameter which are between 0 and 2. Now there is a theorem that tells us the following, and we're not going to prove this theorem, that if A is positive definite, again, remember what was the definition of positive definite, we discussed that in some of the previous lectures. If A is a positive definite symmetric matrix and omega is between 0 and 2, then the SOR method converges for any choice of the initial guess x0. If our real life problem ended up with solving a system with a positive definite symmetric matrix, then we can choose the SOR method with any parameter between 0 and 1, and we will have a convergence. Then there is another theorem which tells us that if A is a positive definite symmetric matrix and block tridiagonal, what does it mean, block tridiagonal? That means that the matrix consists of blocks that form the main diagonal, and then here is another block, and 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 everywhere else is 0. This is block tridiagonal. Tridiagonal is if you have something which may be non-zero on the main diagonal, on the diagonal above the main diagonal, on the diagonal below the main diagonal, and everywhere else you have 0, then you have a tridiagonal matrix. Block tridiagonal means that you have blocks rather than single entries that has the same structure. You have blocks on the main diagonal, blocks above the main diagonal, and blocks below the main diagonal. And everywhere outside of these blocks, you have 0. So if a matrix is positive definite, it is symmetric and block tridiagonal matrix, then several things are true. the spectral radius for the Gauss-Seidel iteration matrix is equal to the spectral radius of the Jacobi matrix squared. Which means that if the spectral radius of the spectral radius of the Jacobi, when it is less than 1, a number less than 1 squared, we will end up with a number even smaller than the original one. So the spectral radius of the Gauss-Seidel will be less than the spectral radius of the Jacobi. Also, you can find optimal choice for the SOR method. What does it mean, optimal choice? You look at the spectral radiuses of the matrices BW, B omega, and you find the omega for which this spectral radius is the smallest, because we know that the smallest spectral radius will give you the fastest fastest convergence. So there is omega in this interval, which will give you the smallest spectral radius. And the formula for this smallest spectral radius is omega star minus 1. And this spectral radius will be smaller than the Gauss-Seidel, the spectral radius of the Gauss-Seidel matrix, and the spectral radius of the Jacobi matrix. Now, how one computes this omega star? There is a formula for this omega star, and the omega star is equal to 2 divided by 1 plus the square root of 1 minus the spectral radius of the Jacobi matrix squared, which is the spectral radius of the Gauss-Seidel matrix. Now, what we can do here is, if we look here, this is BJ. If we look in our example, you remember that the Jacobi, the spectral radius of the Jacobi matrix was 1/2. So we can, and in our example, the matrix was 2 minus 1 minus 1, 2. So the matrix is positive. One can check that this matrix is positive definite. Clearly the matrix is symmetric, and one can show that the matrix, I mean, it's also tri-diagonal matrix. It has an element on the main diagonal, element below the main diagonal, an element above the main diagonal. And everywhere else is 0. It just doesn't have any other terms. And therefore we can compute so this matrix, the original matrix that was for our problem. Let me remind you what the problem was. This was the problem, and the original matrix was 2 minus 1 minus 1 and 2. We computed for this matrix the Gauss-Seidel, the Jacobi, the spectral radius of the Jacobi matrix, and this was 1/2. So one can compute using this formula here. One can compute the optimal choice of the parameter for the SOR method, and so this is 2 over 1 plus 1 minus 1/2 squared, which is 1/4, and the exact number is 4 over 2 plus square root of 3, which is approximately, the value of omega star is approximately 1.0718. And therefore here the spectral radius of this matrix with this optimal choice of omega will be this omega star minus 1, which will give us 0.0718. Which is much smaller than the Gauss-Seidel, which was 1/4, which is much smaller than the Jacobi, which was 1/2, which was 1. And therefore, with this value of the parameter, we will have a convergence much faster than the Jacobi, or much faster than the Gauss-Seidel method. Okay, so that's the end of iterative methods. Next time we will discuss conjugate gradient, and then with this we will finish the numerical methods for solving linear systems. and we'll continue on with other venues. Thank you.